Hello everybody, welcome back to the course on material energy balances. Today we will talk about mixing and solutions. So, what is the importance of this? So, until now we have been assuming ideal mixing and solutions behavior. Now, let us look at how we can account for non-ideality in these scenarios. So, what is the importance of mixing and solution in energy balances? Mixing of two liquids, for example sulfuric acid and water, or dissolving a solid in a liquid can actually release heat or absorb heat. Bonds between neighboring molecules or atoms are broken and new bonds are formed in the product. So, this means there is going to be energy associated with this process. If the energy required to break the bonds is less than the energy released during the bond formation, then the net energy release happens. If you have it the other way, then energy is absorbed. If this energy which is released is not dissipated quickly, then the solution temperature will also increase. In an ideal mixture, what happens is the enthalpy of the mixture is equal to the summation of the contributions of enthalpy of individual components. So, until now we have been assuming ideal mixture behavior. So, that is why we have just been calculating the total enthalpy of a mixture as the summation of the enthalpies of individual components present in the mixture. So, the ideal mixture assumption works well for nearly all gas mixtures, because we are anyways operating under ideal gas behavior most of the times, and for those kind of conditions this assumption is reasonably valid. It also works for liquid mixtures of similar compounds. So, if you have methanol and ethanol getting mixed, this would not be a problem. However, it is not valid for other mixtures and solutions. Heat of solution should be included while we are performing energy balance calculations to account for the energy which is either lost or energy change because of the formation of this mixture and solution. What is heat of solution? The difference between the enthalpy of the solution at a given temperature and pressure and the total enthalpy of the pure solvent and the solute at the same temperature and pressure is defined as the heat of solution. So, this is quite simple. So, think of this as having an initial and final condition. So, initial condition is where the pure solvent and the solute are existing separately at a particular temperature and pressure. Now, the final condition is the solution which is formed. So, just like how we have been looking at phase change, here the process is formation of solution. So, just like how phase change has to happen at the constant temperature and pressure for us to identify the enthalpy associated with the phase change, here for identifying the heat of solution, the formation of solution or mixture has to happen at the constant temperature and pressure. For 1 mole of sulfuric acid in water mixture, what you would have is the change in enthalpy, which is the heat of solution, can be given as the enthalpy of the aqueous sulfuric acid minus the summation of the enthalpy of liquid sulfuric acid and enthalpy of water at that particular temperature and pressure. For sulfuric acid dilution, heat is released from the mixture, and because of this delta H cap, which is the delta H which is the heat of solution, is negative. So, now heat of solution also has another parameter which is the R term. So, what you have here is delta Hs cap T comma R is defined as the change in enthalpy for a process in which 1 mole of a solute is dissolved in R moles of a liquid solvent at constant temperature. See, just like how you have a process where two components are mixing. So, here now what happens is depending on the concentration of one component, you are going to have a different effect on the enthalpy change, and this needs to be accounted for using the R term. So, this is the term which defines the level of dilution or concentration of the solute in the solvent. So, if R becomes very large, then what happens is delta Hs cap approaches a limiting value which is called as the heat of solution at infinite dilution. So, as R keeps increasing, the concentration of the solvent goes up to a very large level, and the concentration of solute is infinitesimally small in that kind of a situation, and this is called as an infinite dilution, and the heat of solution then reaches a plateau and it remains a constant, which is called as the heat of solution at infinite dilution. Heat of mixing is similar to heat of solution, except here you have two liquids that are mixed instead of a solid and a solid being dissolved in a liquid. Perry's handbook gives you an extensive list of heat of solution for various substances in water at 18 degrees Celsius and room temperature. You can also get this information from one of the prescribed textbooks, which is Felder-Russo table B11, where you have the heat of solution at 25 degrees Celsius for HCl gas and sodium hydroxide solid in water, and the heat of mixing for 25 degrees Celsius of H2SO4 liquid and water. R is used in the table B11 in terms of moles of water per mole of solute. It is not moles of solution per mole of solute. So, R is usually represented as the number of moles of the solvent, which is water, per mole of solute. Okay. So, use that appropriately, because when we write the enthalpy table, so just like how we saw with psychrometric charts, if you remember, when we did psychrometric charts, we filled the enthalpy table with only the dry air. We did not write the mass of humid air, because the enthalpy term was obtained for the dry air. It was given in terms of kilojoules per kilogram of dry air. So, the component multiplied with the specific enthalpy term has to be the mass of dry air. Similarly, here this value would have to be accounted for appropriately, so that we use the moles of water and not the moles of solution. Enthalpies in the table are also given as moles of solute, not moles of solution. Again, using the same concept, when you prepare the enthalpy table, you would have to use the appropriate moles for the moles in and moles out, or the moles initial and final. Table B11 data can be used to determine directly the specific enthalpies of solution at 25 degrees Celsius relative to pure solute and solvent at 25 degrees Celsius, which indirectly means that the reference state which is used is pure solute and solvent at 25 degrees Celsius. So, this is given as H cap equals delta H cap S at R, where R is the level of dilution. Another common reference state which is used which is pure solvent and an infinitely dilute solution at 25 degrees Celsius and 1 atmosphere. Instead of using pure solute and solvent, you can also use pure solvent and an infinitely dilute solution as the reference states. If you were to do this, then what you have is the actual enthalpy which you would be looking at would be the enthalpy you get from the table B1 minus the enthalpy at infinite dilution. So, here are a few example problems which would help us understand the fundamentals associated with mixing and solutions. The heat of solution of a solute A in water at 25 degrees Celsius is minus 40 kilojoules per mole A. For R equals 100 moles water per mole of A and minus 60 kilojoules per mole of A for infinite dilution. What is the specific enthalpy in terms of kilojoules per mole A of an aqueous solution of A, for which R is 10 moles of water per mole of A relative to pure water and A at 25 degrees Celsius, and the second component is pure water and an infinitely dilute aqueous solution of A. So, what you have in the problem is you have the heat of solution given. So, one is the heat of solution using pure solute and solvent as the reference states, which is given to you with a particular R value, and you also have the infinite dilution heat of solution. Now, we need to calculate what the change in specific enthalpy would be for preparing such a solution. So, for the first aspect, we need to calculate the specific enthalpy of an aqueous solution of A with R of 10 moles of water per mole of A with relative to pure water and the solute A at 25 degrees Celsius. So, this means the value we have here directly minus 40 kilojoules per mole of A would give us the enthalpy associated with this. So, our H cap would be equal to delta Hs cap at R, and the R is 10 moles of water per mole of A. So, we can directly use this value, which is minus 40 kilojoules per mole of A. So, the next reference state which is used is is pure water and an infinitely dilute aqueous solution. So, in the previous slide we looked at how we would calculate this. So, your H cap would be delta Hs cap at R minus delta Hs cap at infinity. So, this is the infinite dilution. So, what you would have here is minus 40 minus of minus 60 giving you 20 kilojoules per mole of A. So, depending on the reference states we get two different values. Now, let us look at the next few parts of the problem. If 5 moles of A is dissolved in 50 moles of water at 25 degrees Celsius, how much heat is evolved or absorbed? So, first thing we need to know is what is the R value. So, we have defined R value as the number of moles of water per mole of A. So, here we have 5 moles of A dissolved in 50 moles of water. So, 50 moles of water divided by 5 moles of A would give us an R value of 10, which means we can use the value given for heat of solution in the problem directly. So, the Q would be equal to delta H, so which is equal to N delta H cap. So, here we are assuming no change in kinetic energy, potential energy and shaft work. So, this would mean this equation simplifies for the open system to Q equals N delta H cap. So, this would mean Q equals 5 times minus 40, which is minus 200 kilojoules. So, Q here is less than 0, which means heat is not supplied, heat is removed from the system or released from the system. You have 200 kilojoules of heat which is released from the system while the solution is being prepared. So, this is the second part. So, now for the third part we are asked to identify how much heat is evolved or absorbed if the solution prepared is poured into a large tank of water at 25 degrees Celsius. Now, what you have is the initial condition is 5 moles of A dissolved in 50 moles of water. The final condition is what this solution being thrown into a huge tank of water, which would eventually mean the final condition would be at infinite dilution. So, now what we have is the final condition is infinite dilution, initial condition we already know. So, let us try to identify what the change in enthalpy would be, which is Q equals N times delta H cap S infinity minus N times delta H cap S R, which equals 5 times minus 60 minus 5 times minus 40 giving you Q equals minus 100 kilojoules. So, 100 kilojoules would be released if this mixture is, if the solution is poured into a large tank of water at 100 degree at 25 degrees Celsius. So, with this we have done some simple calculations to try and understand what this heat of solution represents. We will also look at more example problems which would help us perform energy balances using heat of solution. So, how would we perform energy balances when we account for solutions? First thing we need to do is we will be preparing the enthalpy table which should consider the solution as a single component and pure substances at 25 degrees Celsius as the reference state. By doing this we would actually have a process where the pure components which are the reference state goes to the final condition which is there in the enthalpy table, which would be the solution of these two components. So, for finding the enthalpy of a solution at a temperature which is different from 25 degrees Celsius, what you would do is you would calculate the enthalpy at 25 degrees Celsius from the tabulated data. You would add enthalpy change for heating or cooling of the solution from 25 degrees Celsius to temperature T. If solution heat capacities are available, this can be used directly for calculating the change in enthalpies. If not, what you do is then you have to calculate the heat capacity of the mixture using Cp of the mixture or use heat capacity of the pure solvent depending on the pure solvent and solute or the pure solvent alone depending on the level of dilution. Here is an example problem where we will be performing energy balances accounting for heat of solution as well. Hydrochloric acid is produced by absorbing gaseous hydrochloride in water. Calculate the heat that must be transferred to or from an absorption unit if HCl gas at 100 degrees Celsius and H2O liquid at 25 degrees Celsius are fed to produce 1000 kilograms per hour of 20 weight percent HCl aqueous at 40 degrees Celsius. Let us now look at how to solve this problem. As the H cap values are available to us in terms of kilojoules per mole, we first need to identify the number of moles of HCl and water in the system. So, the molar flow rate N dot HCl for the HCl would be given as 1000 times 0.2 times 10 power 3 divided by 35.6. So, this gives us 5480 moles of HCl per hour. So, we can also calculate the molar flow rate for water as 1000 times 0.8 times 10 power 3 divided by 18, giving us 44,400 moles of H2O per hour. So, what you have here is the mass of the solution times the mass fraction of the component times 10 power 3 to convert it into grams divided by the molecular weight to finally get the number of moles of HCl or H2O which is present in the system. Now that we have the system, we have drawn the flow chart. So, as you see 5480 moles of HCl gas at 100 degrees Celsius and 44,400 moles of H2O liquid at 25 degrees Celsius are entering to finally form 1000 kilograms per hour of 20 weight percent HCl aqueous leaving at 40 degrees Celsius. Now, let us see how to perform the energy balance calculations. Here no material balances are required. So, we can start performing the energy balance calculations. So, here it is an open system, which means the equation would be Q dot equals delta H dot, assuming there is no change in kinetic and potential energies and no moving parts indicating shaft work is equal to 0. So, because of this we can use this as the equation for the general energy balance. Now, we need to identify the reference states for performing the calculations. So, before we build the enthalpy table, we need to identify what would be the reference states. As we have to use the enthalpy of solution, we will have to use the reference states from the table which is listed. So, the enthalpy table would have HCl gas, H2O liquid and HCl aqueous. So, as I had already mentioned, the aqueous solution is listed as a separate component so that we can account for the enthalpy change from the reference states. So, the reference states would be the pure components as given in the table. So, N dot, which would be in terms of moles, and you would have H cap in terms of kilojoules per mole and N dot out in terms of moles and H cap out in terms of kilojoules per mole. So, you have 5480 moles of HCl gas and 44,400 moles of water liquid entering into the system. So, now you do not have any HCl gas leaving the system or water liquid leaving the system, all you have is the aqueous HCl which is leaving the system. However, when we are writing the component in the aqueous HCl, we will not write the total number of moles, we will only write the number of moles of HCl, because the enthalpy is given in terms of per mole of solute. So, when we use the enthalpy value from the table, we can use only the mass of the solute or the moles of the solute to be multiplied. So, we will account only for the moles of HCl here for performing the calculations. So, this is 5480. So, this would have an H1 cap. So, you have water liquid coming in at 25 degrees Celsius, which is the same as the reference state. So, this would have a 0 enthalpy and this would have another enthalpy which is H2 cap. Now, we need to calculate H1 cap and H2 cap. H1 cap is simple, H1 cap is basically integral Cp dt, where Cp is the specific heat capacity of HCl gas, and the condition goes from 25 degrees Celsius, which is the reference state, to 100 degrees Celsius, which is the state of, this is the temperature at which HCl is coming in. So, using the Cp value for HCl gas, we can calculate H1 cap as 2.178 kilojoules per mole. Now the next step is to identify H2 cap. How do we do that? H2 cap is basically for the process where you have two steps. The first step is you have HCl gas and water liquid at 25 degrees Celsius forming HCl aqueous at 25 degrees Celsius. From here it goes to HCl aqueous at 40 degrees Celsius. So, this is the process. You have two steps. The first step is the formation of the solution and the second step is the heating of the solution. So, this would mean this is delta T and this is the solution formation. So, for the first step we can get the change in enthalpy data using the table which lists the heat of solution. For identifying the heat of solution from the table we need to know the R value. So, R would be equal to number of moles of water per mole of HCl. So, we have 44,400 moles of water for 5,480 moles of HCl, which implies R is roughly 8.1. So, for the first step, which is the formation of the solution from HCl pure component and water pure component, we can look up the table B11 in the textbook Felder-Rousseau, or you can use any other reference book, and you will be able to get this value as H21 cap equals minus 67.4 kilojoules per mole of HCl. For the next value, which is heating the aqueous HCl to from 25 degrees Celsius to 40 degrees Celsius, you need to identify the Cp value for HCl aqueous. So, this value can be obtained from Perry's handbook. So, according to Perry's handbook, the Cp for HCl solution is equal to, for the given mole fraction, is equal to 0.557 kilojoules per mole HCl degree Celsius. So, using this we can calculate the change in enthalpy for the second step, which is integral Cp dt, where temperature is increased from 25 to 40 degrees Celsius. So, this would be equal to 8.36 kilojoules per mole of HCl. So, the total change, which is H2 cap, would be equal to the sum of these two, giving us a value of minus 59 kilojoules per mole. So, from here we can substitute the value back into the enthalpy table and calculate Q dot. So, Q dot, which is equal to delta H dot, would be equal to 5,480 times minus 59, which is the enthalpy of the aqueous HCl leaving the system, minus the inlet HCl which is coming in, which is 5480 times 2.178. So, this value would be Q dot would be equal to minus 3.35 times 10 power 5 kilojoules per hour. So, this is the rate at which heat must be removed for the process to happen. So, with this we have performed an energy balance problem using heat of solution as well. In the next lecture we would have a tutorial session to solve a few more problems which use mixing and solutions, and this will help us get familiarized with these concepts, and it will help us in applying these concepts directly while we perform energy balance calculations. Thank you.